This is Lab F9, Kepler's third law, and this is really similar to the lab sheet that you got. And on the very first one, I'd like you to fill in the other planets. I'm just typing them here. You have to type them yourself, and so on. And I'm going to give you some of the data, but some of the data I will measure. So here you got everything ready for Mercury and for Earth and Jupiter and for Uranus. And I'll show you later on how to calculate that actually. But let's first get some data for Venus and Mars to begin with, the distance and the period. So let's go over here. Here I'm animating that, and that's actually a little bit yet too fast. There we go. I want to see that Venus just hits right there where that corner is of that little box that I have there, right there. There we go. Okay, so let's look at the date here. Starts June 19th, 2010. I'm gonna jot that down. June 19th, 2010. And I'm gonna do the same thing for Mars. Right there. That's good enough. Right there where it's at that corner. And I'm gonna write that down. That's July 10th, 2010. And now we're going to measure exactly one orbit for each one of these two here. My computer had to think here for a moment, that's why it kind of stopped. Okay, right, a little bit forward. There we go. There, that's good enough. That is January 29th, 2011. And now let's measure here for Mars. That takes a while longer. I guess I could accelerate this a little bit. There we go. Quarter of a day instead of just tenth of a day. And right, a little bit forward, right there, that's plenty good enough. Okay, this is May 26th, 2012. Okay, so I need two more data before I go anywhere else here, and that is I'm gonna click on Venus and jot down that it's at a distance of 0.72 AU. It's up here. You can see it looks like 3/4 of the Earth's orbit in diameter, so 0.72 AU. But I'm going to double check if that is actually the average distance. And that was indeed the average distance. And for Mars, I'm going to see if 1.62 is the average. There's that 1.62. And indeed it's not, it's actually 1.52 is the average distance. Okay, here's what we're going to do with these numbers. So I'm going to put this one in here as 1.52, and here it's 0.72, and you could see that Mars is about 1.5 times of Earth's orbit. And now I have to actually figure out how long it took Venus to orbit, and here's the dates that I wrote down earlier: June 19th, 2010 to January 29th, 2011, and that is, I'm just writing this here on the side, and I need some space to write that down. Okay, that looks like it's 7 months. 7 times 30 days is 210 days, plus the additional 10 days here, so that's 220 days. And then I have to see July, August, October, and December have 31 days actually, so I'm going to put an extra 4 days on top of that, so I have 224 days. And then I divide that by 365 days in the year, and that means that I come up with 0.614 years. Sure, I like the number 224 days better. You know, it tells us something, 7 months and a couple of weeks. But we have to have the same units here, so since I put everything down here in years, I have to put it as years as well. So 0.614 for Venus, 0.241, which is a quarter year for Mercury, 1.0 for Earth, 11 years for Jupiter, 83 years for Uranus. That's why I wrote the numbers down the way I do, because they get really large for most of the planets, with the exception of the first two. Okay, for Mars, let's see, for Mars I'm going to come up with, I need to make a little bit more space here. I don't know if I can do this. Not really. So I think I'm just going to take this off here and do this for Mars. The numbers I had jotted down were 7, 10, 10, 2, 5, 26, 12. So that means that is at least 1 year, and then we have boy, this is 10 months. 10 months and an extra 16 days. 16 days. So what I have here, 10 times 30 is 300 days, plus 16 is 316, and then in between I got 31 days, so extra days would be for July, August, October, December, January, March, so 6 extra days, but February in between of 2012, that's a leap year, so I just subtract 1 day, so an extra 5 days on top of the 316, so it's 1 year and 315 days, and again I divide the 315 by 365 and come up with 0.86 plus the 1 year, so 1.86 years, and you can see that that is close to the 2 years that it indicates right here, so I did the calculation correct. 1.86 years. Okay, let's get the data for Jupiter and Saturn. So back to the software, gonna zoom out. Let's see if this is, zoom out further. Whoa, there they are. Okay, I'm gonna take off some of the stuff here, the labels for the first 4 planets, because I'm gonna make it so fast here that those names would just jump all over the place. I'm gonna make this one here much quicker, in the neighborhood of half a year. There we go, and then I'm gonna move, oh, maybe since I did half a year, I'm gonna go to like January 1st, and then I'm gonna move forward. I think what I have to do is Saturn and Neptune actually, and see where we are. And that is actually, whoa, way too fast for Saturn. So let me adjust this here and interrupt. Okay, so for Saturn, and this might be again too fast if I hit the forward button. Okay, right there, just like 1/10 of a year or so, approximately, less than a little more than a month, I guess. So this is November 2043 is what I'm going to write down for Saturn. And now I'm going to move this forward, and whoa, yeah, they're orbiting very fast here. Saturn is virtually done. And I'm going to go through April 2073.